our spin is going the other way. Okay, that's the idea. Okay, so how do we start this whole thing? We're going to start by drawing out a bunch of electron configurations for whatever system we're dealing with. So if we're looking for a d orbital configuration, we're going to start by drawing our 5 boxes and filling them in with the appropriate number of electrons. And instead of just always drawing the ground state as we were taught, we're going to draw every possible one, and we're going to categorize them, and then we're going to group them together. So it turns out like all of these possible options we have for the D1 configuration turn into one set, and we're going to learn how to draw that set. All right. So there's a lot of terminology in this chapter, which is part of what makes it tough. But each configuration that we draw is a microstate. Okay, and the ground state configuration we draw is one of the possible microstates for that overall ground state. We will eventually learn how to jump to our answer. What is the term symbol for our ground state, which is a useful thing to know. That may be kind of roughly what you did at PChem, I think. At the very end, we'll get there. But we're going to start from working from the ground up here. We're going to define some new letters, but they're very, very closely tied to these letters. Okay? I'm going to say new letters. They're new quantum mechanical terms here. So capital M sub L for a given state, this is for a given microstate, capital M sub L is the sum of all the M sub L values for that state. Okay, so for example, if I had a P configuration with 2 electrons on here, and I'm labeling these M sub L values like this, this would be a P2 configuration. It would be the first example we work together. We won't work a ton of these because they take a long time, but we'll try to make sure that we're all on the same page here. So our capital M sub L is just the sum of all these numbers, right? So there's a single electron in a -1, and then there's a single electron in a 0 incremental value, and so it's -1. And capital M sub S then is the sum of all the M sub S values for your state. Little m sub s. Little m sub s refers to each electron, right? Capital M sub s refers to the overall state. So our capital M sub s value for this configuration is what? They're not labeled here, but what do we mean by a little arrow pointing up?
Spin up.
Spin up, and what's its value? What's its M sub s value?
Positive 1/2.
It's 1/2 for each one, and I think it's 1 overall. I heard both of those answers here. Okay. So those values are what we're going to use later. Okay, sort of like when we did group theory, we did all this work and we just got these characters, right? Gamma. It doesn't matter what all this stuff was before that. Once you have your character, that's what we're going to use. So this little picture that we draw, right? This electron configuration picture turns into these 2 numbers. This is a microstate which has these 2 values, and it's not the only one probably that has those 2 values. It's one example of it. Okay. So we're going to tabulate all of these microstates where we're going to record their capital M sub L and M sub S values, and then we're going to put them into a table and figure out how they group together. Okay. And that'll come in a little bit. So let's go ahead and work through an example here where we work through every microstates for a P2 configuration. This gets us through all the details that you'll ever need, this one example, but we'll probably do that with the P2 configuration. So we start with, I do it this way. I know that my M sub L values are going to be -1, 0, and +1. So I'm going to have 3 boxes that I can put electrons in. There's going to be a lot of these. I draw a long column here. Okay? And each row is going to have its own values of capital M sub L and capital M sub S. So let's start where we were a moment ago, this box. That's exactly what we just saw. Okay, so this represents 2 electrons in the first 2 boxes that are of 3 possible. And so our capital M sub L is -1, and then added to 0, right? So it's -1 overall, and our m sub s is +1, the two 1/2s add together, right? So this is just, again, what we just did. And what we're going to do is just move the electrons around into every possible position. Okay? So every row is a new condition. So here's one where I try to be systematic here. I kind of hold the left one and I move everything else around, right? And then I move the left one over and I move everything else around. And that way, when you do it systematically, will give you every possible configuration. So what are our values now? M sub L is what? 0, right? It's -1 + 1, right? M sub S is still 1. And in fact, it will be every time I leave my arrows just both up. So my last configuration, I've kind of run out of things to do while holding this left one where it is. So I move it over a box, and I find there's only one thing to do. Okay? Because if I put this other electron to the left of me, I've already done that configuration. That's the first one, right? So it's just kind of like I work from left to right here. So this one has a capital M sub L value of +1, still the spin is 1. Okay. All right, so then we go, maybe we'll do this one next. So these are the other ones where the spins are aligned, not paired, not opposite. So this one has a M sub L value again of -1, but now our M sub S is -1, right? Because both spins are down, it's -1/2 and -1/2. Keep going. This is 0 and -1. This follows a definite pattern. I'm repeating the M sub L values from what I just did with the inverted M sub S. And we can sort of think of this as its own category, right? Up here was its own category. And now we're about to switch to another new category. So one thing we might do next is now the spins, we've done everything where the spins are aligned, right? Everything's spin up and everything's spin down. We'll find that all of these things are part of the ground state because this is what Hund's rule taught you to do. Okay, this is one of, so we'll find. Later on here, we're going to find the complete set of Hund's rules, not just that we tend to maximize spin of ground state, but there are other parts to this as well. But anyway, Hund's rule taught you to draw a configuration something like this with the spins aligned somehow, but it didn't tell you what boxes to put it in because actually all of these are part of the same state. If you find a ground state, it's all of these at once. All right. What we might do next is pair them up into one box. So what are my numbers now? Capital M sub L is what? -2, and M sub S? 0, right? Positive and -1/2. And in fact, from now on, my M sub S value will be 0 because again, I've done everything aligned, so they're always going to be opposed, and it's always going to cancel out. Okay, so let's just go ahead and hop these through each of the 3 boxes that I can have. So this is now a 0, 0 state, right? And then finally down here, it's a +2, 0 state. Now I've done everything I can do like that, and so now I move them to 2 separate boxes. There's different ways you can go about figuring all this out, but anyway, this is how I'm doing it. So I'll have a spin up on the left, and I'm going to watch what happens as I move my spin down one around. This is all different states, right? This state is unique. It's different from each of the other ones. It looks kind of like them, but it is different. And it is also different from the one, as we'll see later, when I have the spin down one on the left at the -1 spot, and my spin up one in the 0 spot. That's a different state. It's distinguishable. All right, so what's my M sub L now? -1, yeah, and then still 0, of course. Okay, so I'm going to go through again. I'll go kind of quickly here. 0, 0, and then I'm going to move here, and that's +1. Okay, and I run out of things to do with my electrons in this way. I not find anything else to do with having a spin up one to the left of a spin right one. Spin up is to the left of a spin down. So I reverse it now. I do this. So this is back to -1, 0. And then I have down, up over here. This is 0, 0. And then I have down, up, this. And that's a +1, 0. Okay. So there's some pattern to this. And as we build our table, you'll be able to tell if you missed one somewhere. Okay? Because it'll not be symmetric or something like that. Let's see where we're at. And I'm going to show you how to sort of compile these into a table. I think I've covered them all here. I don't think there's anything else we could do. You may approach it differently. You may like each time you draw one of these, draw its like opposite one, right? Instead of up down, it's down up, for example. That would work fine. However you approach it is fine. But this is how I do it. It works for me. What we're going to generate now is a microstate table, and this is the step right before we get to those crazy term symbols like doublet P. Okay. all this is a sort of collection of these states here, represented now not by like specific states, but just by little x's. We're just marking there is one of these. And it's just it's two axes, so you have capital M sub s on one, no matter how you do it, but this is the traditional way, capital M sub L on the other. And so our M sub s values that we'll ever see, you need to look back at your states and see, right? But we have +1, we have 0, and we have -1, right? It's a range, you know, sort of like if you have a total L value of 2, for a quantum number, you have M sub L values that range from -2 to +2. Here we have -1, 0, and +1 possible. And our M sub L values, their highest value is 2, and their lowest value is -2. This will always be the case, they'll always be mirrored. Okay? So we have +2, +1, 0, -1, and -2. So our table's going to look like this. Sort of grid it off here. Give ourselves place to mark where conditions occur. So we just start from the top, it doesn't matter. So we have a state which is an M sub L value of -1, this row, right? And we have an M sub S value of +1, and so we have a little x in that box. Okay, that's all we're doing. And so if we look around, we're staying with M sub S of +1, but it goes from an M sub L of -1 to 0 to +1. So we have 3 x's, right? And then we jump to the next set, and now we're at M sub S of -1, right over here, right? And we have a -1 M sub L, a 0, and a +1. All right, so we've dealt with the first 6. It's just these 6 x's. So we keep going, and now we're just going to go down this 0 column, right? Because everything here had spins opposed, and they canceled out. So we go to -2. This goes pretty fast. So it goes -2, 0, and 2, right? That's weird. They're all spaced apart, but we're going to fill in those bits here now. So it goes -1, 0, 1, and then again, -1, 0, 1. All right. And there are some patterns that will always emerge here. Okay? You'll always have more x's in the middle than you have on the outside. And an interesting thing is the number of x's you have in the middle box is the number of terms that you have. Those are the number of collections that we label with letters and numbers like this. So we have 3 terms that contribute to this, one of them being our classical ground state. Okay, so what we need to do now is collect those terms, and this is a process, okay? You want to work from the outside in, knowing at the end you have to find 3 answers because there are 3 x's in the middle, whatever the middle is, there be 4 middles. This is an odd number, 3 different ones. You have a true middle, but you can have 4 boxes, right? And there's 2 in the middle, right? Don't start in the middle. It's hard to tell sometimes how many things fit into that state, but you start from the outside, and what you have to do is generate a set which spans from whatever your positive M sub L value is, it has to span to that same number on the opposite side, and whatever your positive M sub S value is, it has to span to the other side without having an empty box, right? So I can't start here. There's nothing here, right? So there's no state that encompasses this entire table. But I can start here at a 0 value of M sub S. That's my largest value of M sub S. And it's going to take me from a +2 all the way down to a -2, okay? So I'm going to draw a box around that. I'm going to actually cross out my different x's. I brought some extra colors today just for this reason here. Okay? That big box right there represents a single state, okay? And by marking that off, I'm just going to sort of, this is just bookkeeping here, right? But I'm just going to kind of cross out one of these x's from each of those boxes. Okay? And those are the x's that contribute to that term. We'll name it in a little while, but this is one of our sets. So we've eliminated, 5 of our different states out of however many we started with. All right, so now again, I start from the outside in, right? And I have to find a box that's, symmetric somehow, that has a range. You can see from +1 to -1 is possible here, right? And also from +1 M sub L to -1 is possible. So that's my box. I'm going to draw it around that whole set. And there has to be an x everywhere in here. If you're missing an x, you've missed a state. That had to be the case. Box this whole thing off. My second of 3 states, again, because I know I have 3 x's in the middle, and I'm crossing one out each time. So now I'm going to cross out an x in every single box that I just marked off. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them in a 3 by 3 box. And that leaves exactly one X left, right? So I work from the outside in, I look around, I see no unaccounted for microstate out here. The only one that's left is right in the middle, okay? And that crosses out my last state. Which one of the 3 X's is it? I have no idea, right? And in fact, quantum mechanically, I think that there's no difference, right? There's 3 states that have that value of angular momentum somehow, right? Coupling between the L value, the M sub L value, and the M sub S in the way that we drew. But weirdly, what it means is that our ground state for this thing, this is P2. Our ground state, we represent like this, right? And this would be, this -1, 0, +1 or something, right? So this would be that X, which we represent, right? -1, 0, -1, yeah. So the total spin is +1, right? And our total angular momentum is -1. That configuration I drew is that X, right? It's one of this set. And then, if I flip everything over, then I'm in this set where the M sub S is -1 instead of +1. But weirdly, there's some that have M sub S values of 0, right? Which somehow means in the ground state, these things are opposed, right? And this is not at all obvious, but somehow one of these configurations that looks like this would have a M sub L of -1 and an M sub S equal to 0, right? That's this box, and this is part of the state. At least there's a couple ways to get there, but this is part of that state. The other one is where you flip those 2 arrows around, right? I just make the inverse, down, up instead of up, down. But one of those 2 is part of the ground state, weirdly, right? And it doesn't look like it could be the same energy based on what we understand as Hund's rule, but that's what the microstate tables tell us. Don't worry about it, but it's just a weird fact. And weirdly, the other state of those, that one or its inverse, which would be, just for clarity here, this would be the inverse with exactly the same quantum numbers, right? The other one of these pair here, which look identical, is part of a different microstate, or a different term, I should say. All right, so let's talk about naming terms. They're named like atomic orbitals, okay? Using quantum numbers, M sub L. So so we're actually kind of like naming an orbital backwards. Like, if we know what its M sub L value range is, right? Let's talk about orbitals first. So let's say, I'm just going to kind of do this on a board. I don't want this on a note here, but trying to show you, you already actually know this stuff. It's just kind of backwards from the way that you had learned it. So if we know that our M sub L values range from -2, what orbital are we talking about? What's its L? What must be its L if this is the range of M sub L? Right. Okay. We're about to do the same thing. And in fact, we're going to name something capital L, right? Which is the highest possible value of L, right? Because this defines its range. We say that M sub L ranges from negative that number to positive that number, right? So if we look, we see that there are these values of M sub L here that range from -1 to +1, right? Those are defined by some capital L, right, which is a quantum number that defines the possible values of M sub L. And that's what our term symbol is named after. Let's write that down. L, capital L, equals M sub L max for a set of microstates as we just boxed them off. Now, M sub S, our spin state, ranged from -1/2 to +1/2 for a single electron, right? What we never bothered to define, because there's only one value of it, would be an S, right? S would be the value which this spans, right? It's the maximum value of M sub S. It's the same pattern here. L is the maximum value of the M sub L series. S is the total spin, right? The total spin is what gives you these range of possibilities for the little spin states there, right? Anyway, so we have an M sub S range here of +1 to -1, right? And so there's an S, a capital S term, which we use in our part of our name, which is the M sub S max, again, for a set of states. So for each of these boxes, we're going to figure out what L and S are. Okay? I'll mark them right near our table. So for this big blue box here, what is L? Right, you look at the top box, the highest value you have on this axis for that set. And what is S? Look on the M sub S line, you see what's the possible maximum value? 3, or I'm sorry, 1. So L is 1 and S is 1. Okay, for this set, what are L and S? L is 2, S is 0. Right? And for our middle box, right, our maximum spin is 0, our maximum M sub L is 0. So again, the L here is kind of what's the range of angular momentum values. S is what is the range of spin values that couple is in. So that's the simplest case. All right, so we have 3 terms that we've defined now in this example. Just gonna write them down here. That's one of them, the middle box. The next one might be L equals 1, S equals 1, and then finally L equals 2, S equals 0. All right, so we're going to name these again. I'm trying to just convince you. You've already done all this work before, right? If my L is 2, how would I name an atomic orbital like that? Be D, right? Lowercase. Everything lowercase for atomic orbitals, everything uppercase for these terms. This is all backwards because it was these terms that allowed us to name those orbitals in the first place. It was seeing the spectroscopy that allowed us to understand what the orbitals were. So these little letters are like the smaller version of what was originally named. So what we're seeing now is actually the original, weirdly. So when L is 0, what kind of orbital is that if it was an orbital?
S.
S, right? So we use a capital letter, capital S. And then up here to the left of it is the multiplicity. Two ways to think about this. There's a formula. 2s plus 1. This s being spin, this s being the orbital name. Okay, it's a little confusing, sorry. But this s here is the total spin. So you double s and add 1, right? So 2 times 0 plus 1 is 1. Okay. So this is called a singlet s term. Another way to think about that is how many boxes are there for spin, right? There's a single box for spin. There's a single value for spin. It is 0. Okay. Let's use this next one, L of 1 and S of 1. So if this was an orbital, atomic orbital, what would its letter be?
P.
P. And then you double 1 and you add 1, so it's 1 times 2 plus 1, that's 3, so it's a triplet P. Or you could say, look, there's 3 boxes here, right? There's 3 spin values, that's a triplet. Because when you do this, when you measure this spectroscopically, it splits into 3 signals, okay, under a magnetic field. You'll find this peak will split into 3 signals because it can work with the field, it can ignore it because it has no spin at all, they cancel out, or it can be opposed, right? So you get split into 3. That's what it means. Triplet P. And then finally the last one, name it.
D.
Singlet D.
S is 0, so we're going to have a singlet here, just like before. 2 times 0 plus 1. And then L of 2 gives you a D orbital. So it'd be a D term, right? There's some history to these letters. Remember it sometimes, not always, but this stands for principal, this stands for diffuse. I think this stands for singular or something. These old words that just people were describing the pictures they saw when they looked at spectra, because they had spectra way before they understood what the heck they were seeing. Singlet D. So we're just about done. But with just these letters, I mean, so what this tells you is that if you were to look at an atom with a P2 configuration, we might think of this as being carbon, okay? And I'll show you, I have the real data for carbon somewhere, with the real numbers that you find if we were to look at a spectrum. But what we would see is 3 peaks, okay? just from the p orbitals alone, not even talking about s to p and all those other things, but the p orbital transitions alone, or I guess the ground, it's a little hard to describe. Electrons transfer from one orbital to another, right? So they have to have some place to go, but they have three different starting points, right? One of them being what we call the ground state, and this should look like one of the ground states. We know this answer, right? This is going to come back. Part of Hund's rules. But then there are other excited states that still are just from the P configuration itself. And so one of those might be, this is a unique state, because that state that I just drew is this little X right there, right? And so that one we know is part of some other term. We know it's not part of the ground state term. It has to be separate, right? And that thing would represent some excited state. It's got pairing energy, and it's got some other stuff going on. It's got some problems, right? It raises its energy relative to these ground state terms somehow. All right, so we're going to try to put them in order, or at least figure out our ground state and then sort of guess at the other ones, but we'll be wrong some of the time on this. And it's that ground state term that kind of drives everything. This is a long process to get there, but we're kind of trying to understand what does that ground state term look like, not for p orbitals, but eventually for d orbitals, because again, we're trying to get back to the metal complex spectroscopy. So, so to figure out the relative energies of terms, we rely on the complete set of Hund's rules. We're going to write those out. There's just three of them. There's a couple other rules that come up, selection rules regarding what transitions are possible from one state to another. But this is Hund's complete set of rules. So rule one is the ground state has the highest possible multiplicity. Okay? These are in order. So this is the most important rule. So multiplicity was that 2s plus 1 thing, right? So it's this little singlet, doublet, triplet, whatever. So in our case, we have a triplet and we have two singlets. The triplet is our ground state because that's rule one. If you have a highest value here, you're done. So the second rule is if there's a tie, then the highest value of L, the highest angular momentum, is your ground state. Okay, and then there is a third rule, and it involves something we haven't defined yet, which is the total angular momentum. Remember, I was talking about spin-orbit coupling, right? You have angular momentum that's related to L, and you have angular momentum that's related to S, and they could be additive or subtractive, and so that's what we do, is we just do all the different combinations of those, right? We'll write it down here in a second. Well, let's leave a little space there. I'll define it first. Okay, so J equal to total J for a given term. This is for a given term, so maybe our doublet P state or something like that, or what was it, triplet P? J is equal to L plus S. These are the capital letters, right? The maximum values. Comma, L plus S minus 1, comma, L plus S minus 2, etc., all the way down to the absolute value of L minus S. These are always positive numbers, always positive numbers. So let's look at our triplet P. Here we do have a little range. So L was 1, you can tell by the P letter, right? And S was 1, because somehow this number doubled and added 1 to it, gives us 3. So L plus S is 2. Then we subtract 1 from it, and we're going to go all the way down to L minus S, which would be 1 minus 1 is 0, right? And it's just integer values in between them. The absolute value didn't do us any good, but sometimes it does. So L plus S all the way down to L minus S. There's 3 values, meaning that if you, this is the fine splitting now. Okay, so this single peak here, if you apply a field to it, you can see this is really why it's a triplet. Right? Triplet means 3 things. Here's the 3 right here. These are the three peaks you would see, and they're just slightly different in value. So here, our last rule for Hund's rule is if there are multiple, and there were in this case, if there are multiple J values, this is angular momentum values for a state, meaning it's not a singlet. If it's a triplet or a doublet or whatever, you're going to have multiple J values. There are two ways. If less than half filled, so half filled meaning, a p orbital can hold 6 electrons total, so less than 3 electrons, 1 or 2. The lowest J is the ground state. And if more than half filled, added detail, probably not super important compared to the grand scheme of things, but few electrons, little j, that's the correlation there. Let me just show you a real spectrum. We'll sketch it out together here. For carbon, which is a p2 configuration, it also has s orbitals. The p electrons is what we're looking at, those transitions. So we would think of its p electrons as falling into something like this, right, for carbon. This is its gas phase. It's pretty high energy, 25,000 inverse centimeters. It's way outside of UV. This is like deep UV. Never seen it. But what we see is all spectroscopy, all these spectra of inorganic compounds are always written in inverse centimeters. Just get used to it. It looks crazy, but that's what we have. Okay, so somewhere, the ground state being defined in this case as about 0, we have 3 little values very close together. So one of them is 0, and this one is our triplet P. Since this is only less than half filled, so our ground state is the one with the minimum J value. So this is triplet P. So our ground state is that triplet P with the lowest possible J value. That's how we note it, is that down there as a subscript. Our next state would be a triplet. It's at around 16 inverse centimeters, so very, very close to 0, but slightly higher in energy is the triplet P1 state. And then slightly higher than that at around 44 inverse centimeters, weirdly they're not equally spaced, is the triplet P2 state. Okay. And we go way up here to around 10,000, somewhere up here, is the singlet D state. 10,194 inverse centimeters, and then way up here, it turns out is the singlet S state, which is at 21,650. I didn't draw my scale perfect there, but that's the spectrum. So it's backed up. Well, I should say we derived this whole model from the spectroscopy, right? This is data. This is our results. Our discussion is we're interpreting this as being collections of microstates. We think we're maybe right. Okay. So how do you tell which of these is first? It looks like the higher angular momentum comes before the lower angular momentum. It looks like higher multiplicities come below lower multiplicities. It doesn't exactly work. There's a lot of complexities there. You can guess that. I would accept it. I'm just going to suggest that's what we do. So we'll follow Hund's rules after the ground state. So the ground state is the thing with the highest multiplicity. If there's a tie, look for the highest pedal. Right? If you keep going to the next state, then you look for the next highest multiplicity. And if there's a tie, you look for the next highest L, right? Which is what we found. So the highest multiplicity was triplet, done, ground state, right? And then we had 3 J values, so the lowest of those J values wins, right? And we go and put them in order. And then we go to the next highest multiplicity, but they're both singlets, right? And so we go to the next highest L, and it works. But it doesn't always work. That's okay. Let's take a brief detour from this microstate table. So we need to be able to do all these things eventually, and it's quite a lot. It's a long process, right? You start with just this idea that I have 2 electrons in p orbitals, so I figured out their values, and so I put them in every possible box. I draw a gazillion terms, you know. For a p3 configuration, this like, it's like a squared, it's like, it goes up exponential. That's a factorial relationship, okay? It goes up like crazy with big numbers. So like d5 is just completely insane. I've never worked it. I probably never finished, right? You know, for the small numbers, you know, d2 we could do, it's just more boxes, and so you end up with more and more and more terms possible. And this, you know, this microstate table gets pretty big because it ranges from pretty large numbers, right? But you can still do the thing. So I'll assign you a problem that will take a little while to do, or will take some time to do. It's just a bigger version of this same picture here. But let's take a brief detour and show you how to get to at least this answer. Like I can say very quickly, to ground state. Because we know how to draw a ground state electron configuration. And if we draw it in a certain systematic way, it's going to predict for us the ground state term symbol. So let's go to this problem we just worked. We know that the answer to this problem is a triplet P, right? And we could even say it's a triplet P0 term. But how could we get there without drawing a whole microstate table? Well, what we do is we maximize spin, following what we think of walking into this class as Hund's rule, right? It's really just part of that set of rules that predicts the ground state. But we maximize spin, and we too maximize M sub L. It's really capital M sub L. Okay? And if you do both of those things at the same time, you've just figured out, what you've really done, is you've figured out the answer to this box, the one with the highest M sub S and the one with the highest M sub L, right? And this defines your ground state term. Because this is the thing with the highest multiplicity and also the highest angular momentum, right? It's going to be your ground state term. So if I draw my boxes out at -1, 0, and +1, and I try to maximize the spin, meaning they're both going to be spin up, right? That's maximizing my spin. And I also try to maximize my M sub L by pushing them all the way to the highest boxes I can while still following that first rule. My first electron will always go in this box no matter what, because that is the biggest angular momentum and the highest spin I can have for one electron. And here's my second electron, right? Where I have to put it, right? So my M sub L is equal to 1, and my M sub S is equal to 1, right? And this defines my triplet P term. Because this implies that my L is 1, and this implies that my S is 1, because I've done everything I can to maximize those two values, right? This is a single microstate, not a term at all, but it's a single microstate that represents that maximized value. And it's all you can do, it's all you can predict. It's just that ground state only. Let's try it for some other configurations, and I'll show you in the book. They have a bunch of these tabulated. Chapter 11. Worth some quality reading time here. This is pretty dense, but the book does an excellent job, I think, on this. It's very detailed. It goes through the whole thing just like I did. Language will be different. But like there's this table for D configurations, right? You'll see like D5, look at all these things. Doublet, quartets, more doublets, some more doublets, some quartets, and a sextet S term. So where's your ground state in this whole thing? Yeah, the sextet S, right? It's, 6 possible spin states. This is D5. We know what it looks like, right? Let's see what happens there. So 1, 2, 3, 4, 5 d orbitals. Their L values range, their M sub L values range from -2 to +2. So let's try to predict that ground state. We're going to find the answer is sextet S. So 1 electron goes here, we maximize spin and L, right? M sub L. So 1 goes there, we keep all the spins up, and we just fill sequential boxes, and we have 5 electrons. We know that's the ground state of a D5. And in fact, it's a unique ground state. Anyway, I guess they can all be spin down as well. That's part of it. But anyway, it's an S term, meaning there's only 1 box. Like an S orbital has 1 box. If I calculate my total L, it's, you know, the -2 and positives cancel, and the 1s cancel, and the 0 is 0. So I'm 0. And my total S is 5 times 1/2. Right? And so what's my term? L0 is an S orbital, right? So we double 5/2, and we add 1. It's really best to use that rule here. So we have 5 left, and we add 1 is sextet. Right? So it means that there are sort of 6 spin values possible in this particular diagram. 3 on the right and 3 on the left, right? From 5/2 to -5/2 with integer units between them. That's how it works. And this is my my ground state term. Interestingly, let's think about, so the Hund's rules, if we look back, it's a good example to work on. If there are multiple J values, if it's less than half filled, the lowest J is the ground state. If it's more than half filled, the highest J is the ground state. But I never mentioned what happens if it's exactly half filled, right? And it turns out there's always just a single J value when it's half filled. And this is an example of one of those, exactly half filled. Right? So my J here is going to be just a single value. You don't have to choose. But let's see how it works. So it's L plus S all the way down to L minus S, absolute value. Right? And one of these numbers is 0. So it's going to be, yeah, we'll see here. So I have 0 plus 5/2, right? 0 plus 5/2 is 5/2. And then all the way down to the absolute value of L minus S. And the absolute value of 0 minus 5/2 is 5/2. Right? So I really have no range because this thing needs to be more than 0. And the absolute value of 0 minus 5/2 is equal to 5/2. So I have only one value. So this is my J. I don't know if that makes sense, but that's the formula. So we're stuck with it. If either one of these values is 0, I don't think spin can ever be 0. There's always 1. It's always 1/2 at least, because electrons, never mind. Yeah, you can have 0. Anyway, sorry, if any one of these terms is 0, then you have no range of J values. We would find that back here with the singlet D term, for example. This was L of 2, S of 0, so 2 plus 0 is 2, right? And it goes all the way down to 2 minus 0, which is still 2. So there'd be a little 2 there. There'd be a little 1 here because L was 1, right? Sorry, L is 0. Okay. I think I went off on too deep a tangent there, but our ground state is a sextuplet S, and its only angular momentum value is 5/2, so I was trying to get to that. And that would be a horrible problem to work, because you saw how many states there would be. There would just be so many microstates there. I don't know. There's some factorial equation that I can never remember, but it's a big one. And it depends on the number of electrons and the total value of L, which determines the number of boxes you can have. And some of these would repeat as if they were a total, so you have to subtract those out of again. Some mathematician worked out how that works. But this is a very handy thing to do. This is something I'll ask you to do, predict the ground state for a given configuration. Let's do another one just for the heck of it, D7. At this point, we're talking about what are called free ion terms. You know, previous chapter, we were talking about these splitting into T2G and EG. We'll get back to that. So these are the metal atoms before they have been affected by a field, a free ion, just an ion floating in space, or an atom floating in space. So D means we have 5 boxes. Positives 2, 1, 0, -1, -2. And just take a moment here, it's a good exercise. Find the ground state. Follow Hund's rules. Maximize spin, maximize angular momentum. I'm going to ask the person writing the least to have a question. And you're done. Man, that'd be fast. it's very, very possible, and I'd say likely in spectroscopy terms, to go way beyond D, F, right? And then it just goes alphabetically, right? So if you have L values. So S, P, D, and F have historical names, and then after that they gave up. And they just go alphabetically, G, H, I, J, K, etc. What's happened? I don't know what F means. You know what F means? The letter F. Historically, you don't know all this weird stuff.
No, I don't know.
Principal, diffuse, probably German. That's my go-to. Okay, so what is the term symbol? Who has it? It is F, meaning that you have a total angular momentum of 3. Right? What's its multiplicity? 1, 2, 3, 4, 5. We might start there, 6, 7. Actually, this is like backwards because my spin is down here, but it's okay. We're just going to use our sort of maximum spin here. It's an F term, and we have 2. So let me think about this now. Yeah. So it is these 3. Get myself confused. Yeah. So okay. So our L value, right, is all these upward, like here, everything canceled, right? So it's just these 2 spin down ones that are contributing. Contributing. It would be a 3 for L, and our total spin is these cancel, so it's 3 times 1/2, right? Right. And so our total multiplicity is 3 halves times 2, which is 3, plus 1, which is a quartet. So we should see that in our handy-dandy table here. So D7, they say same as D3. Okay, that's their answer, because they don't want to write it all again. But look at that, right? Essentially, all this stuff that happened over here canceled out, right? You have the spins canceling out. Weirdly, the 3 that matter here are this D3, and they are what contribute your total angular momentum, which is -2 and -1. Your over would be +2 and +1, right? And then our total spin is based on 3 electrons. So the D3 configuration had all this stuff. It had a doublet T, a quartet P, and a quartet F. Well, there's the quartet F that we found, right? And the quartet P is another thing with high multiplicity, which maybe is the second state up. Okay.
Can you one more time explain the equation for the 4?
Oh, 2s plus 1. 2s plus 1, right. What it means, always, is that that's the number of possible spin states that are in that term. And so our spin, our maximum spin is 3 halves. This is why 2s plus 1 works. So you have 3 halves, you have 3 halves minus 1, which would be 1/2. You have 1/2 minus 1, -1/2, and then -3 halves. Those are the possible s values you'd have for that term. There are 4 boxes. Quartet. But 2s plus 1 predicts that there are 4 possible options there. Okay. Yeah, so that's the idea. We made it through that. Let's take a little brain break here. And we'll do another microstate table example next time, and then we'll go a little farther and get into how to use this in inorganic complexes. And to get there, we'll also have to talk about selection rules, what transitions are possible. Trying to figure out what. Yeah, I'm going to have you tackle a simple version of one of these problems on this assignment. Really small, like no bigger than what we did. There are not many options for me. Okay. But I want you to just get used to drawing out microstates and making a table. And it'll have the end of chapter 10 on it as well.